Faster flow usually sounds like a great thing, right? I mean, more production equals more revenue. But if you push the velocity too high in a sand-producing subsea well, you aren't just moving oil faster. You're actually, quite literally, sandblasting your own pipeline wall from the inside out, just one tiny particle at a time, every single day, for years. And remember, this hardware is sitting thousands of feet underwater. It's not like you can just walk down there and patch a leak. There is a hard physical ceiling that you just cannot cross. And calculating that precise speed limit, well, that's the entire point of this explainer. Let's get right into it.
So we have this fundamental conflict between economics and physics. The math seems simple at first glance. Faster flow means more revenue. As an operator, you obviously want to get as much product from the reservoir to the host facility as fast as you possibly can. But nature imposes a really strict physical limit on that production. You see, subsea engineering isn't just about managing liquid, it's about managing a multi-phase mixture, which almost always includes solids, like sand. If you push that speed limit too hard, you cross a threshold where the fluid stops acting like a simple transport mechanism and starts acting like an abrasive water jet. And that will absolutely destroy your multi-million-dollar infrastructure.
So the crucial point here is understanding exactly what this speed limit actually is. We call it the erosional velocity, or VE. Technically, it's defined as the calculated maximum allowable flow velocity in a line carrying entrained solids. Basically, it establishes the absolute ceiling where mechanical wear becomes totally unacceptable. And I want to be really clear about this. This is a hard design ceiling, not just a soft recommendation. Think of it kind of like pressure washing a concrete driveway. A gentle stream cleans the surface, right? But if you crank up the pressure and the volume, you actually start tearing chunks out of the concrete itself. Sand-laden production fluid does the exact same thing to carbon steel pipe walls, just over a much longer timescale.
Okay, moving on to Section 1, the geometry of destruction.
You know, erosion isn't just about how fast the fluid is moving. It actually depends heavily on what that fluid hits along the way. I want you to pause for a second and think like a subsea piping designer. Given identical flow velocity and identical sand content, which component do you think is going to wear out faster? A long, straight pipe run or a standard elbow? Same fluid, same speed, same sand.
The answer is the elbow, every single time. Here's what a lot of people actually miss. Erosion isn't primarily a straight pipe problem. It is a geometry problem. In a straight run, you get what we call random impingement. The particles just make glancing contact with the wall at a really shallow angle, so you get very low wear. But at a 90-degree elbow, you have direct impingement. The fluid is forced to change direction abruptly, and those heavier sand particles, which carry way too much momentum to just turn smoothly with the fluid, slam head-on into the pipe wall. Think of it like putting gravel in a garden hose. Point that hose straight at a wall, and the gravel just bounces off at a shallow angle. But force it through a bent hose, and every piece of gravel violently impacts the outer curve of that bend. That's exactly why elbows, T's, and chokes are the absolute highest risk zones for structural failure.
Which brings us to Section 2, calculating the velocity ceiling. To give engineers a defensible, rock-solid basis for how hard they can push production, the industry relies on mathematical models. The Salama and Tulsa models are two of the most prominent ones out there. And notice how both of them evaluate the exact same critical variables to assess the risk. They're both looking at the size of the sand particles, the total sand production rate, the density of the fluid, and the geometry of the pipe itself. And they both output the exact same critical metric, VE, that maximum allowable erosional velocity. The whole underlying mechanism driving these models is that erosion damage is not linear. The wear rate increases sharply, exponentially actually, the moment you cross this calculated threshold. Just to give you a concrete sense of scale here, for typical sand-producing service, this maximum allowable erosional velocity usually falls into a remarkably narrow window of about 10 to 20 feet per second. The American Petroleum Institute standard, API RP14E, gives some foundational guidelines on this. But whether you're pushing closer to 10 or 20 feet per second depends heavily on your specific conditions. Like, are you dealing with sharp angular sand grains or smoother rounded ones? Is your carrier fluid a high-density liquid or a low-density gas? Regardless of the fluid, though, staying under this specific ceiling is an absolute daily operational mandate.
Let's look at Section 3, the time trap.
There is a massive trap hiding in these calculations. A system that is perfectly designed on day one can actually fail catastrophically years later, even if the operator follows all the rules perfectly. This timeline lays out exactly why. Look at year one. The well is operating safely. The reservoir is fresh, and sand production is incredibly low. Your flow velocity is well under the calculated ceiling. Everything's great. But fast forward to year 10. As the reservoir ages, pressure drops, and you might get water breakthrough. the geological formation itself begins to weaken, which leads to a significant increase in the sand rate, sometimes arriving in these sudden massive bursts. So by year 15, your fluid velocity might be exactly the same as it was on day 1. It's totally static. But because the sand volume has skyrocketed, your previously safe velocity now suddenly crosses the threshold into severe mechanical erosion. So the variables in our erosion models aren't fixed. They change over the life of the field, and that means a static engineering design will eventually be defeated by a dynamic, aging reservoir.
All right, Section 4, Managing the Sand Threat.
So if sand production is inevitably going to increase and our pipe geometry is literally fixed on the seabed, how do we actually prevent catastrophic failure? Well, we have a few mitigation tactics in our arsenal, but every single one comes with a distinct trade-off. First off, you could simply reduce the production rate to lower the velocity. But of course, that directly cuts into your field's revenue. Nobody wants that. Second, you can redesign the pipe system proactively. Instead of using standard elbows, you can use what are called blind tees. These basically force the fluid to cushion itself, which greatly reduces that direct sand impact we talked about earlier. Third, and I find this engineering paradox fascinating, you can increase the pipe's wall thickness to give it a longer wear life. But listen to this warning. If you make the pipe wall thicker on the outside, it gets heavier and way more expensive. But if you make it thicker on the inside, you reduce the pipe's bore. Shrinking the inside diameter actually forces the fluid to travel faster. This increases the velocity and can potentially make the erosion rate even worse. It's crazy, right? Finally, for the most vulnerable spots like chokes and sharp bends, engineers will just abandon standard carbon steel altogether and use specialized highly erosion-resistant materials like tungsten carbide just to withstand the punishment. To summarize everything we've covered today, erosion is fundamentally mechanical wear from solids. It's a strictly physical destruction process. Sand acts as an abrasive, systematically chewing through the steel wherever the fluid is forced to change direction. Managing this requires incredibly precise calculations and just a constant, ongoing awareness of how your reservoir is aging. We've spent this entire explainer talking about what solids do to your pipeline. But I'll leave you with a provocative thought. What if your production fluid is perfectly clean? What if it begins eating through the steel wall, completely destroying the pipeline with absolutely zero sand in the stream? That, my friends, is the silent, purely chemical threat of corrosion. And that is exactly what we'll be diving into in our next explainer.